I want to welcome everybody to the March meeting of the Canadian Vintage Radio Society of Alberta. It's nice to see a good crowd today. And you probably came in anticipation of Gerry's talk, so this is excellent. It's going to be on capacitor testing and ESR. And I guess he has a historical exhibit as well, so we're going to find this very interesting from a number of perspectives. So we'll let Gerry just take over the show.
We all have one thing in common, the ability to test capacitors as to just how good your capacitor is. Now, the inspiration for my talk came out of January's Nuts and Bolts magazine, and the actual meter this guy built is actually shown on right on the cover of the magazine. And what it's based on, and this pretty much applies to any component. When we were in school, whether it be university, tech school, self-study, we always looked at a capacitor, for example, as just a capacitor, but when you actually break the capacitor down, it's got several other elements built into it. So for example, there's an equivalent series inductance. And again, you've got leads off your capacitor, leads inside the capacitor potentially. This forms a bit of an inductance. It's not a lot, but it's still there nonetheless. So if you wanted to really dig into the theoretical nuts and bolts of the capacitor, you could take that into account, plus the series resistance again, your wire leads and so on and so forth, finally up to the capacitor plate. And then at the same time, you've also got between the capacitor plates your parallel, which is more to the point, your leakage resistance that you'll find with the capacitor. So if you actually look at this little drawing that we've got on the board here, Murray alluded to it in the newsletter. What could be more simpler than a capacitor? Two metal plates with an insulating dielectric between them. And so typically when a capacitor fails, very seldom do you see mechanical damage to the plates or even the leads connecting to the plates. Most often your failure mode is in the dielectric. So if you think back to the old paper capacitors, even if you used low acid paper, eventually over time you will get a breakdown in the dielectric. Even though it might be dipped in wax and it might be well sealed, nothing is ever permanently sealed. And especially in Alberta here, what's the one nasty thing we've got in our atmosphere that we don't really pay a whole lot of attention to?
H2S.
H2S. Yep, there is traces of H2S around. If in doubt, check your wife's silver collection in the china cabinet. You'll see quite often it tarnishes quite a bit. The point is, you do get contamination in the electronics, and if you get a breakdown in the protective cover and the breakdown of your dielectric, eventually the capacitors do happen to fail. Now in the case of paper capacitors, you've got degradation of the paper. But let's say this was an electrolytic capacitor that was liquid filled. So the liquid tends to dry out over time, which is why when we typically recap a radio, the first thing we do is change out the electrolytics, because they do have a tendency to leak with age. Has anyone got some horror stories on capacitors they want to share? Yeah, Radar.
I know if you hook them up backwards, they go off like one of those ships exploding. What pairs aluminum?
Yeah. Yeah, exactly. Polarity on electrolytics is important. I remember years ago I was doing some electronic service work. I replaced an electrolytic capacitor about this size. I'll pass it around. But when I didn't put it in backwards, but I put in the wrong voltage rating. It wasn't sufficient to the voltage. So after running for about an hour, I was letting the circuit burn itself back in. I was in the office next door doing up the paperwork, and all of a sudden I heard what sounded like a 22 cartridge going off. And it was one of these capacitors that had actually blown itself open. The circuit was still working. Managed to power everything down, take out the defective capacitor, put in the proper capacitor, and start my test regimen all over again. But that is one of the things about capacitors, is that if you don't test for them, you can get some catastrophic failure.
There's an interesting experience too I had in that an ordinary non-electrolytic capacitor was, I think, a plastic film capacitor or something like that. Been in a radio for years, but tested perfectly all right on any of the tests at low voltage. But in the radio, when you're running at about 150 volts or something like that, it would break down and leak only at that higher voltage.
Yeah.
So it convinced me right then that any exhaustive capacitor testing should include some kind of leakage at voltage ratings in order to be really sure that you're testing for all aspects of breakdown.
Yeah. Yes, in the back, sir.
One thing I ran into fixing a filter predict the TV gate for a guy was those little brownish red Chinese capacitors that you see quite often now. It was marked 0.039, but it measured 0.44 microfarads. It was in the vertical oscillator, which didn't run properly.
Yeah. So incorrect markings on capacitors now.
I don't know if that was it, or it was just bad right from new. It's hard to say. And now I check every single cap for value, especially on TV when it plays 100.
Oh, exactly. So when it comes to testing capacitors, again, we've got a wide variety of test equipment here, including my Amprobe digital multimeter, which actually has a capacitor testing range starting at 4 microfarads all the way up to 4,000. So I'll just pass that around, let you guys take a look at it. So your new digital multimeters today even have the advantage of testing some capacitors. And again, Rick was kind enough to bring in some of the stuff, some of the test equipment he's used over the years. This one notably out of China, where it's just a couple of microprocessors, a couple of surface mount components, a display and a push button, along with a mounting spot for the capacitor where you can actually test the capacitor. And let's see, what is this one coming in at? 16 microfarads with an ESR of 7.3 ohms and a voltage loss of 9.2%. So I'll just pass that around. So again, that's a fairly neat little trinket. And then we've also got this Heathkit Capacitor. So some vintage equipment from days of old. I'm not going to pass this or the BK or the solar around after the presentation. By all means, feel free to come on up to the table and take a look at this. But again, you look at the solar. Again, with the solar, we've got the ability here to test for, you said leakage up to about 400 volts. So that would have helped you out, Marie, when you were testing that film capacitor, because that is one of the interesting things about the ESR tester that I built out of Nuts and Bolts magazine, is that it is a low voltage test situation. It doesn't actually test the capacitors under, if it's a 100 volt capacitor, it isn't going to test it at 100 volts. But this B&K analyzer along with the solar will actually do that. However, this machine actually tests the capacitors right up to the highest voltage level possible. But the interesting thing about testing for ESR is that what you have to do is you have to eliminate, there's my markers. What you want to do is you want to eliminate any effects from the capacitor itself, where you're left with just the pure ESR, which will give you a resistance reading in ohms. So again, what this circuit does, and I'll pass this around and show it to everybody in a minute, is it takes an internal oscillator running at 100 kilohertz. And at 100 kilohertz, what it does is it swamps whatever capacitor characteristics are, leaving just pretty much the resistance, which goes into the capacitor under test through a detector, and then a meter driver rectifier right to an old needle movement meter. Now, you could also jazz this up a little and put a digital meter on this thing, but that involves an extra power supply and a little bit of tinkering with this board. What I did is I got in touch with a CVRS member who actually had a couple of these meters sitting in his junk box, and for basically a printed circuit board, we actually horse traded a circuit board for 2 meters. So I've got a meter like this sitting at home in my own ESR unit, and then I put this unit in here, this meter in here. This ESR test unit actually belongs to the Vintage Radio Group. Now, the interesting thing about the internal oscillator is that if you're testing other capacitors and the testing requirement requires a different frequency, you simply put your frequency source into this BNC connector, flip the switch into an external oscillator mode, and set the voltage level at about 1.8 volts peak to peak. And using that external oscillator, you will be able to get a decent ESR reading off the capacitor that you're testing in question. And that's pretty much all there is to it. It's actually a relatively simple piece of test equipment. The thing I liked about it is that it only took an evening to put together once I had the circuit board designed, and all the components are readily available. So for some reason this board developed a problem. You can still get a TL082 JFET op amp to this day. The regulator is a standard 3-terminal regulator. The only chip that's really funky is the -5 volt generator, because in order to run the JFETs you need a -5 volt power supply, but the 7660 IC chip that's commonly available out there is what was used in this circuit. And again, if it should ever die for some reason, getting a new one isn't going to be all that relatively difficult. So I'll just pass this around. Feel free to take a look inside. From a safety aspect too, the power supply comes off basically a little wall wart at 6 watts. So again, if there was ever a short inside the unit or inside the capacitor under test, you shouldn't have anything catastrophic happen on your test bench. So the neat thing about this piece of test equipment is, in reality, it's meant to supplement either a tester like this or like this, where you actually want to bring the capacitor up to its operating voltage to see what the leakage is going to be. But this ESR will at least test and see what your capacitor is doing, because as the capacitor starts to age, typically what will happen with the dielectric is a failure of the dielectric is that it'll show an increase in its value. So instead of being at 1 or 2 ohms or 3 ohms or whatever the spec happens to be on the test sheets that you get from the manufacturer, it could go a whole lot higher. When that happens with the higher resistance, the component tends to heat up. And as it heats up, it becomes a less efficient piece of equipment inside your circuit. So if you've got issues with things like motor boating or whatever the case might be in your radio, again, this is why we just default change out the electrolytic capacitors. Yes?
How about a tantalum check out there?
Good question, Bill. I've never tried it.
Okay.
I would say it would probably test out okay. One of the things you do have to keep in mind is that this is a polarity sensitive device, so you want to make sure you hook the capacitor up properly. And then on top of that, make sure the capacitor is discharged before you actually put it in the circuit. So
the tantalum is very low AC resistance.
Yep. Correct.
With a regular capacitor.
Yeah. And the article in Nuts and Bolts there does talk a little bit about the tantalums. I've forgotten what it said, because basically when I saw the circuit was easy to make, I designed the circuit there using TraxMaker, and the circuit board that you see in there is my own homebrew design. And
what's in the detector? Is it a diode or is it a special circuit?
it's let me just pull out the circuit here. If I'd have had time to put this on a PowerPoint, we could actually look at the circuit on the board. The detector uses 2 stages of an op-amp through a resistor capacitor network, and there's only one detector diode, and it's a 1N4148, so it's all low signal. It's all low signal stuff. And then from there it goes into a meter driver off another chip, which then goes into a diode, basically a diode bridge to drive this meter. So there's so you can calibrate it to different levels as well too, because there is, let's see, there's one calibration pot to set the output of the oscillator, and there's also another calibration pot here for calibrating the meter. So if 1 to 5 ohms doesn't do it, you could theoretically recalibrate the circuit to go to a higher resistance test if you wanted it to. So, yes, Murray.
But now most ESR bridges, ESR meters, use an AC bridge. Is that detector circuit in this one a type of AC bridge?
Yes, it is.
Oh, okay.
Because again, what's coming off the oscillator here is a 100 kilohertz sine wave.
Right. And why would you need an external oscillator then?
In case you're testing a capacitor that basically requires a different test frequency. Like he used 100 kilohertz because that's the standard he saw. But if you happen to have a special capacitor that requires, say, 50 kilohertz or 150 kilohertz, uses some other kind of AC testing frequency for their ESR. So your point, Bill, tantalum capacitors, they may require a different ESR test frequency. There's the ability to put an external oscillator into the circuit, fire it through the detector to your capacitor under test, and you can read your ESR that way. Yeah.
Well, if you varied your frequency, 100 kc, would it make a difference reading on your ESR?
I believe it would, but again, I'm just one of those things where I built the circuit and basically followed the recipe in the nuts and bolts article and let the results speak for themselves. Yeah, it's quite a cute little gem for the test bench, because if I remember correctly too, with the 100 kilohertz going in at about 1.8 volts, you should theoretically be able to test a capacitor in circuit. You shouldn't have any external effects from other circuitry components to give you any goofy readings on your ESR meter. Any other questions? That's some good questions here today. Saying this is what keeps me out of trouble at night. Yes, Les?
Just wondering about the RP.
Uh-huh.
You're ignoring it, are you? Can you measure it?
Well, theoretically, what it does is that if you...
Could you not measure that with a DC voltage?
Yes, you could.
That'd be much higher.
But what they're
Really high.
But what they're doing with the RP and the RS is they're combining them to create your ESR. So
RP is very high.
yes, it should be high. But if your capacitor is defective, guess what?
Probably a more significant factor in
Yeah.
some of the circuitry. If you've got a lot of leakage, you might want to be able to measure it separately.
Yeah. That's a good question. And again, what I've typically done in the past when I didn't have access to all this test equipment is I would just take my digital meter on ohms and I would check the ohm reading of the capacitor. And the neat thing is then you could actually see it actually charge up.
Yes.
In fact, Fluke had a little information leaflet that basically said if you could actually time how long it takes for the resistance to charge up to a certain point, you could do your T equals RC and actually calculate what the capacitance of what you were testing was.
That's exactly how that little Chinese meter does it. It puts a DC voltage on and times how long it takes to get up to a certain threshold.
Yeah. So.
And that's how it determines the value.
Yeah. So that's another way as well too. So it's but that's because we're doing And for that, that's because we're doing at a DC, where now if you're doing AC, guess what? Everything now, let's see, this disappears. You can pretty much assume it's 0, so it's almost like a short circuit, so we'll short that out. The 100 kilohertz basically shoots through the capacitor and provides a little bit of resistance, but not a whole bunch. So at the end it just becomes a parallel combination of your RP and your RS to form your ESR, is the way I interpret it. And that's the interesting thing about electronics. It's not, we'll go through and we'll calculate things to 6 or 8 decimal places where required, but when you're getting components that have a 1% value tolerance nowadays, and what did some of the old resistors go? Plus or minus 20%. Some of the capacitors, 20 to 50%. Even though we tried to get it down to a textbook value, Real Life 101 then steps in and says, well, you might need 47 microfarads. I'm giving you a 46.5 microfarad capacitor today. That's just the way it worked out. You didn't win the lottery and get 47.000. Be nice, but I also don't feel like spending $1,500 on a capacitor just to get that exact value, because it, again, we're putting these in the circuits where, even though we're using exact mathematical analysis to come up with a working solution, at the end of the day it's still an approximation. A fairly decent approximation, but that's the difference between theoretical that we learn in school and practical that we're actually applying day to day, whether it's repairing an old tube radio or actually building a new circuit or rewiring a house. Any other questions or comments? And thank you for your time. Thank you for coming out today and supporting the club, and I'll turn it back to Murray. Thank you.
Well, thank you very much, Gerry, for a very interesting presentation.